Oh, I should have mentioned it. I forgot to mention it. Let me write here, or let me just, after this, you write one line. We call F inverse U the inverse image of U. Okay, this line. This is known as the inverse image of U. Okay. So now we see that these two are quite different sets, and we are going to write that, mention that. Note that the forward image of this and the inverse are quite different sets. So there is no reason for them to be, for thinking that they are equal. Also, there is one more thing, and which is f of f. Okay. What about this? Suppose we apply f inverse of 1, 2, 3, and on that we apply f. What do we get? We have already calculated this. This is 1, so f of that is nothing but, since we are taking 2 times the value, so this is 2. Keep in mind, see, there is one more thing that I must mention here. F of 1 and f of this are two entirely different things. F of 1 is the value of the function or the output of the function when 1 is the input, and this is an element of y, the range. However, this is a singleton set, and this is the forward image of this singleton set, and by definition this is not an element of n, this is a subset of n. Although they may look like the same thing, but they are not the same thing, strictly speaking. Okay, so this is 2, and you see that this is not equal to 1, 2, 3. So applying the inverse image and then applying the forward image on the result does not get us the set back. We usually end up with something else. Later we will see that whatever we end up with, that is actually although it's not equal to the original set, but it's always a subset of the original set. We will prove that. Okay, now let us take another example. That one, that same thing, informal. So this is example 3, 4, 6. Let f from the set of integers into itself be this function. Okay, so now we are going to calculate the inverse image of this. Then inverse image of what? Inverse image of the set that we do, this set. See, calculated this forward image of this set, because the function is the same, no, this one we previously had here. Forward image of this set is this. Now let us calculate the inverse image of this under F. Then F inverse of zero, 1, 4, and it turns out to be equal to this set. Why? How? You see, you have to collect those elements whose squares are in this set. So that means effectively what we are to calculate are the square roots of these numbers. And the square roots can be both, I mean all the possibilities, negative as well as positive, not just the positive square root. Square root of 0 is 0, square root of 1 is -1 and 1, square root of 4 is -2 and 2. So just to remind us of what we did previously with this function, we calculated this forward image and it turned out to be this set. Now we calculated the inverse image and we have got a bigger set than this one. You see, -2 is there in this set, but -2 is not here in the original set with which we started. So from this we can conclude something like this. So we see that F and F inverse do not quite invert each other. They are not exactly inverse operations. They are in a special case. We will come to that later. And also there is one more point. Also, note that we do not need F to be bijective in order for F inverse U to make sense. If you recall the definition of an inverse function to a function, you see we have already seen that whenever a function is bijective, it's both injective and surjective, one-to-one and on-to, then it has an inverse function. And this is the only case when the function has an inverse. Looking at this notation, we should not confuse ourselves into thinking that this notation means that F has to be bijective. No, inverse image of a subset of the range is definable or is defined for any function, not just bijective functions. And its definition is there, and that definition does not involve does not have anything to do with the fact that F is bijective or not bijective. We don't need that. Even without having a bijective function, F inverse of U makes sense. So let us just write the other thing also. I mean, here we calculated the image of the inverse image of a set. Now we are going to do the reverse. I mean, we are going to switch F and F inverse. So that means we are going to calculate the image first and the inverse image afterwards. So image of what? Let us take this set. Keep in mind that our function is the square function. So this set is 0, 1, 4. And as we have seen here just now, this is -2, -1, 0, 1, 2. So you see the difference here, and this is also not equal to the original set. The difference between this situation and this situation is now clear. Here also we don't get the original set back. Here also we don't get the original set back. But here we get a subset of the original set, and here we get a superset of the original set. Here the set we end up with is smaller. It is inside the original set, and here the set is bigger. It contains the original set. Okay, and these two things are general results. We are going to prove them at one point. Okay, now there is a remark after this. Okay, now we are going to consider bijective function. Let f from x to y be a bijective function, and let u be a subset of y. Okay, so u as usual is a subset of y, but now our function is special. It is a bijective function, not just any function. Then we have apparently two different meanings for the same notation. It may seem that creates a discrepancy. Then we have two apparently different meanings of F inverse u. We can think of F inverse u as the inverse image of u, which is what we know F inverse u as, the inverse image of u under F. But we can also think of F inverse u as the forward image of u under F inverse. So see this peculiarity. Since F is now bijective, its inverse function exists. So on one hand we have F inverse of U as our usual inverse image of U under F. But since F inverse itself is a mapping, we can also think of F inverse U as the forward image of U under the function F inverse. So there are apparently two different meanings. Now the question is this a discrepancy? Fortunately, this is not a discrepancy. However, both the meanings give us the same set, and this is an exercise. This is the first exercise. Where we have to show that actually we have the same set, no matter which interpretation we follow. Okay. Now we go to something else. As remarked earlier, functions are not sets. We have already said this. Functions are a different type of objects. They are not sets. But since functions are considered to be a type of object, we should be able to consider sets of functions. Recall the very first axiom of set theory that we have been doing all these things for so long. The first axiom is that sets are objects, and the main point of that axiom is that calling something an object means that it has the potential to be an element of some set. So the first axiom says that since sets are objects, they can be elements inside some other set. Okay, so to allow for that, we are calling sets as objects. Now, while introducing functions for the first time, we said that functions are also a type of object. So they can be elements of some set, and that's what we are going to consider now. So that's what we have written. Since they are considered to be a type of object, we should be able to consider sets of functions, sets whose elements are functions. In particular, we should be able to consider the set of all functions from a set X into a set Y. But to do this, we need to introduce a new axiom into our set theory, and this is the 10th axiom. Okay, before we write this, however, can we quickly recall what the axioms were, just for the sake of refreshing our memory? You see, how many axioms have we had so far? There is that first axiom that sets are objects. Okay. Then the second axiom is that there is an empty set. The third axiom is the axiom of singleton sets and pair sets. They exist. The fourth axiom is the axiom of pairwise union. If we have two sets, then their union is a set. The fifth axiom is the axiom of specification, which we discussed today. The sixth axiom is the axiom of replacement. We can replace the elements of a set with some other objects. The seventh axiom is the axiom of infinity. It ensures that there is an infinite set, and this axiom actually contains in itself all the piano axioms, and it contains in itself the system of natural numbers. Okay. Then we have the eighth axiom, the axiom of universal specification. And this particular axiom led to the Russell's paradox. So this axiom cannot be introduced into set theory. We have already seen this. The ninth axiom is actually the one which helps us get rid of Russell's paradox, and that is the axiom of regularity. If you remember, it said that if we have a set A, then there is at least one, a non-empty set A, then there is at least one element X in A which is either not a set or is disjoint with A, and that turns out to be sufficient for us to avoid Russell's paradox. So now we have the 10th axiom. I brought these things back just to refresh our memory, to consolidate all the things. Okay, so now the 10th axiom is the axiom of power set. Although power sets themselves will not appear here in the axiom itself, but in a corollary, in a consequence, in a result that is a consequence of this axiom, we will see that power sets exist. So let X and Y be two sets. They may or may not be equal. Okay, so two sets are given. Then there exists a set whose elements are functions with X as domain. Should I write it like this, or okay, let me change it slightly. Then there exists a set denoted by this somewhat strange notation. This notation may be somewhat unfamiliar to some of you, but we will see why we have this notation. There is a reason for this. Denoted by this, which consists of all the functions with domain X and range Y. Thus, f belongs to this thing if and only if f is a function with domain X and range Y. That is, in other words, f is a function that looks like this. So this is the set of all such functions. And now to explore this concept, we are going to take an example. Okay, the sets are somewhat strange, but still, okay, let us just see what it says. Let the power is gone, x is equal to four comma 7 and y is equal to 0 comma 1. Then the set this consists of these four functions. The first function maps both 4 and 7 onto 0. Okay, this symbol means maps to. 4 is mapped onto 0. That means if the input is 4, output is 0. If the input is 7, output is 0. Okay, so that is the first function. The second function maps 4 onto 0 and 7 onto 1. The third one maps 4 onto 1 and 7 onto 0, and the fourth one maps both 4 and 7 onto 1. So this set consists of these four functions. They are the elements of this set. Okay. Yeah, now the reason for this notation. The reason we use the notation is that if the set Y has n elements, that is, it's a finite set, and the set X has m elements where n and m are natural numbers, then this set has n to the power m elements. That is primarily the reason that we use this strange notation y, and then as a superscript we have x, n to the power m elements, and we will prove this. In the sixth section. This is the fourth section, right? So in the sixth section, which treats finite sets, we will prove this. Specifically, we will prove this here. See, proposition 3, 6, 14 part, it has many parts. So part F deals with this. Okay, now we come to the question of why we are calling this as the axiom of power set. A consequence of axiom 310 is this. Is it lemma or yeah, it's lemma. Lemma 3, 4, 9, I think, yes. Let X be any set. Let me continue from here. Let X be any set, then the collection of all objects y such that y is a subset of X. This collection is a well-defined set, and this is what you know, or we know, as the power set of X. Okay, and the fact that this is a set, it follows from axiom 310. However, the proof we will not do now. We will the proof actually is an exercise, so we will do it when we solve the exercises at the end of this section. So in place of proof, right now we are writing C exercise 6. And now regarding this set, we have a remark, obviously, and this is remark. The set y such that y is a subset of X in the previous lemma is known as the power set of X and is denoted by this symbol 2 to the power X. just like that one, this notation also has a reason. For instance, if A, B and C are distant, okay, wait, if A, B, C are distinct objects, then the power set of this consists of these sets, all the subsets of this set. First of all, the empty set, then the singleton subsets, then the sets consisting of two elements. I think I won't have space here, I will continue there, comma, and then finally the set itself, because that is also a subset of itself. So this is the power set of this set. Okay, all the subsets of this set are available.